Well, let's see what we can screw up today on the bench. So, can't take yourself too seriously, folks, because if you start taking yourself too seriously, then maybe other people will start taking you seriously too. Anyhow, so I have everything connected up, and I'm trying to keep things as basic as possible. I have two 8-ohm dummy load resistors. All they are is, a resistor, and they're on a piece of aluminum channel to carry away the heat. These will not even get lukewarm. There is not anywhere near enough power in this amplifier to overheat these. So I could run this all day and it'll never even get warm. I have found a transformer that I don't think is adequate for this, but it's all I have. And it has an output of 36 volts center tap. So it puts 18 volts AC from center to either side, which is the recommended. That's what they recommend there. They said AC 12 to 18 volts. Well, long story short, so I totally messed up on my camera work, and probably over half of this video was lost. And it was simply because I wasn't paying attention to what I was doing. I am not a camera person. I am not a videographer. I am somebody with a camera that, I push the button and record, and I push the button and stop recording, and, I don't go beyond that. So anyway, we're going to do this whole video over again. Hey, you got to laugh at yourself. It must have been foreshadowing when I made those comments at the beginning of this video, and yeah, that part actually got recorded. So yeah, well, what can we learn from this, Tony? All right, let's start over. So first things first, I found out during that video that this transformer just is too undersized, as I thought it would be. And it was getting warm. It was providing the amount of power we needed, but it was really getting warm, and I didn't want to damage this. It's a good transformer, it's just too small. So what I had to do was I went to this one, which is a lot bigger, but it's a couple volts too high. Instead of an 18 volt transformer, this is like 22 volts center, or 44 volts or 45 volts center tap, something like that. So I just used the variac on the circuit breaker, the electronic circuit breaker, and I just cut the power down to about 102, 103 volts, and that gave me exactly the amount of output that I need. No harm, no foul. Down the road, if we get to a point in this series where I do some improvements on this circuit, one of the improvements we'll make is to be able to put a little more voltage into this and be able to use this transformer, because this is what I have and I don't want to buy anything because this is just a project. You know what I mean? All right, let's get back to what we were doing. So what we are going to do in this video, if I haven't already said it, we'll see after I do the editing. If I'm repeating myself, I apologize in advance. We're going to use the oscilloscope, and this is not an oscilloscope video, by the way, folks. I did a whole series on oscilloscopes, what the knobs are, what the buttons do, and the switches and all that, how they work. Go back and go into my channel, hit the search, the magnifying glass thing, search, and just type in oscilloscope. You'll see all kinds of videos. So we shouldn't have to repeat that. What we're going to do is we're going to use the scope to look at the waveforms on this. And particularly, we're going to look at the differential pair signals. And there's one part of this that we're not going to be able to look at with a scope, and that's right here at the output of this input pair. And the reason being is that because this is such a small signal, and because it's such a high impedance signal, my oscilloscope is not, and most oscilloscopes are not going to be sensitive enough to be able to read this. When you use even a 10 times probe, you're putting a 10 mega ohm load across this with respect to ground, and that really messes things up at this point. So what we're going to do is we're going to measure at the output of our voltage amplification stage. But really what I want to show is how these two transistors interact. So this is going to be your non-inverting input, and this is going to be your inverting input. And if you remember from the last video, we did a few voltage measurements and wrote them down. And I was only using something like plus and minus 12 or 14 volts or something like that. I didn't have a whole lot of voltage on here. But anyway, you could see kind of how this all worked. And I talked a little bit about how this circuit was biased, and how when we're looking at these transistors, now this is a little bit of a repeat, but the way this thing turns on, the way an NPN or a PNP transistor works, is they don't really care about ground. A lot of people get hung up on ground, you know, hooking, measuring everything to ground. But remember, this is a split power supply, meaning you have a positive voltage and a negative voltage. And in the middle of that positive and negative, you have a ground, or a common point. And when we're looking at this transistor, you're not looking at this with respect to ground, but you're looking at, is this more negative in charge than this? So as long as the emitter is more negative than the base, current will flow. So even though this is ground, this is 0 volts, negative voltage is more negative than ground. So current will flow. So this resistor actually sets that up. Now you have 0 volts here when you measure it, but you still have current flowing through here. So if you measure from here to here, you'll measure a voltage drop of, as we did, of 588 millivolts. And then as we apply a signal to this, it'll go either positive or negative voltage, which will change this right here, and that it'll follow it up here. And since we're picking it off of the collector of this NPN transistor, it is going to not be inverted. In other words, it'll be in phase with what's at the base. And we're going to just use the scope to look at all this. And we're going to look at, what do you think this gain is? What do you think the gain is going to be on this first stage? Do you think it'll have gain, or do you think it'll be unity gain, or what do you think it's going to be? Let's take a look. Okay, the first thing we're going to do is right up here at your input, we're going to put a 50 millivolt RMS signal at 1 kilohertz. So we're just putting a 1 kilohertz, and 50 millivolts is a pretty small signal. And we're going to feed it right in here into the input of Q2. So this is our Class A input amplifier. And let's just see what this looks like. It should be 50 millivolts, right? RMS. So I have it connected here, and I'm just connecting it right at the junction of R2 and the base of Q2. And you can see there's R2, there's Q2. And let me go up here. And if I turn the signal on, I'll turn the amp on first. Okay, turn the signal on. And let me see here. And let me adjust my scope. And see, I'm on the highest sensitivity there. I'm only on 5 millivolts per division. And remember, being that this is a times 10 probe, because if I set this probe to times 1, if I put a direct probe in there, I'm only going to put a 1 mega ohm load across there. And that's going to adversely affect the signal. So you have to have times 10 probe, which dramatically reduces the sensitivity of your scope. But anyway, there's what you have, and it's going to be a 50 millivolt RMS signal. Now if we move our probe over to the junction of R12 and Q4, and if we look at the signal there, you'll see that it's identical to the signal on Q2. And the reason being is Q4, that R12 resistor, is actually connected directly to the outputs, or your output transistors. So that's what your speaker is seeing right now as well. So your input, this whole amplifier it is a non-inverting amplifier. I don't know, some of you that watch a lot of my videos, some of the Marantz gear and so forth, they actually will invert the signal. It has to do with the design of the amplifier, but this one does not. So you can see that is coming straight from here. There's your speakers. Go to this. If we follow this back, there's your output transistors. There's your driver transistors. It comes straight through, goes through this R12 and right into this. So these two signals are identical. They're in phase with one another, mostly in phase. They're ever so slightly out of phase because of the delay of this loop, but that doesn't really mean anything in audio frequencies a whole lot. It can at certain points, but typically not. And what do you think that's going to do to this then? If we look at the signal down here, let's look at our emitters. So we're now on R8 right here and R8 right there. You can see it's once again the same signal. So you can see that this whole input pair has no gain to it, really. There is no forward voltage gain in this amplifier, or in this in the input pair. Now a lot of people think that this input pair has gain, but it doesn't. And this just proves it. The signal is the same the whole way through, from here all the way. Now, why do you think we would want to do that? Why couldn't we just take this signal here and connect it right up here, right? Well, it's because these two pairs are looking for differences. So if there's a difference between what's on this base and this base, it will add or subtract to the signal up here. And that's really the magic behind this, because that's what the negative feedback does. We're going to see how that affects things here down the road. But believe it or not, it's because of the component setup here that everything is balanced right now. And we're going to throw it out of balance later in the video, but let's just now look. Now again, like I said, I can't look at this because my scope won't allow me, but we can look right here. Let's see what happens to that signal after it goes through Q6. So I'm going to connect it right to the base of Q8 and the anode of D4. Okay, we're now connected right here, and you can see there's D4. And look how high our signal is. I have to go way down to get my signal, and it is actually 100 times higher than it was. So you could see I was on 50 millivolts per division. This would be 500 millivolts per division. This is 5 volts per division. So you see how much gain that little voltage amp stage puts onto this thing. And that's why it's called voltage amplifier. That's why it's called the VAS stage. Okay, now let's look at, we're going to leave channel 1 on here, and then we're going to go into dual channel mode and put channel 2 of the scope right here. So we're going to look at what's going, so this is your push-pull output, and this is called a SEP, or a single-ended push-pull design. So let's take a look at what the signals look like going in here. Now, of course, we already know what this is. What do you think this is going to look like here? And we're just going to compare them over top of one another. So here we are on the two ends of the diode string, the bias spreader. And you can see I have these two traces spread apart so that you can see the individual signals. Let's turn it on. And you can see they're almost identical. As a matter of fact, they are identical, and they fall right on top of one another, and they're even in phase. And you might say to yourself, well, Tony, why are they in phase? How can this be a push-pull amplifier if they're both in phase? Well, it all has to do with this circuit here, these drivers. Do you notice a difference between them, the two drivers? One of them is an NPN, and the other one is a PNP. So this works off of negative voltage, and this works off of positive voltage. And what do I mean by that? Well, what I mean is in an NPN, the emitter has to be more negative than the base. Whereas in a PNP, the emitter has to be more positively charged than the base for current to flow. So you can see, even though this is an in-phase signal, these are going to drive equal and opposite. And that's what's going to allow these two output transistors to go either more, this one makes it go more positive, this one makes it go more negative. And at the center point, you have 0 volts. When these are both turned on the same way, you're going to have 0 volts. As the waveform swings positive, this is going to respond to that, and it's going to turn this transistor on more, and this center point is going to become more positive. If I go on the negative half cycle, this will go more negative, as will here. This will eventually turn off. This whole side will turn off, so there will be nothing coming from the positive. This will become more negative, and you'll start getting negative voltage at the center point. And that's how a SEP design amplifier works. And by the way, this is called quasi-complementary because you have NPN transistors on the outputs. We could very easily convert this to a full complementary just by putting in a PNP transistor here, and we may have to make a couple little changes, but for the most part, you could drive this with a PNP transistor here too. Now the reason that we do this is it's easier, in the old days anyway, it was easier to have two of the same transistor have similar characteristics. Back then they didn't have the processes to make an NPN and PNP complementary pair that both had the same exact characteristics. They were very different from one another. As technology improved and we were able to get complementary pairs of transistors, it made a big advantage. Notice this one, the emitters are connected like in a Darlington pair. And in this one, it's more like a Sicali or Sickley pair. So you have two different types. In other words, this one, you have two voltage drops controlling this. And in this one, you have one voltage drop here, and then you have from the base to here is one voltage drop to the center. It's different. So you could see that that's a disadvantage, but by changing how you do the design, I went over this in the last video, by these resistors, you can kind of compensate for that a little bit. Okay, for the last part of this video, what we're going to look at is R12. We're going to look at this 33K feedback resistor. This works in conjunction with R10 and C4 to set up this feedback, what I call the feedback signature. And what you want to do, this is a filter network here, and this is a very specifically chosen value of resistor. And it was designed that, if you notice, these were together. And this whole setup is going to make sure that these two stay the same, or that these two stay the same all the way throughout any frequency within the audible spectrum. We'll look at that later, but right now, let's just look at the influence that this has. Okay, I now have the scopes connected back to the input, the base of Q2 and the base of Q4. And what I'm going to do is, if you notice, I have these jumpers across R12, which is this 33K. And I've just taken a 47K resistor. And right now it's not connected. But what we're going to do is we're going to go back and look at these. And we know they're the same, right? They're both the same signal. And I'm going to put a jumper. I'm going to jumper that 47K across here. And we're going to observe what happens to these two signals as I do that. Okay, now don't mind the noise on here. That's my scope. So if you notice, they're about the same. And they're slightly different because of how the scope probes are interfering with the circuit. And if I go here and I jumper that in there, do you see what happens? Not a whole lot. Just a little bit. It changes that one channel. See that? Now that doesn't look like it made much change at all, did it? Neither here nor here. It was just the tiniest little change, right? But if I go back over to here, to this line right here, the output of our voltage amplification stage, and remember I have to turn my scope way down now because there's so much gain here. Let's see what that does when I put that resistor in there. Okay, here's our output, and this is the output of the voltage amplification stage. And watch what happens when I jumper the resistor on there now. Big difference, isn't it? See that? Resistor in, resistor out. So you can see that resistor actually does have a big influence on the output of Q2 at its collector. Now remember, transistors are current-controlled devices. And that is a constant current circuit in there, source. And when we measure everything, because of how our meters and everything, or our scope probe affects that, we can't really measure up there. So I have to look at the output of the VA of the voltage amp stage. But you can see it does make a big difference on Q2, what signal you put on to Q4. That's the whole principle of negative feedback. The more feedback we put in, because of course, reducing the resistance of R12. So reducing the resistance of R12 allows more signal to get to here, right? That's all I did. By putting that 47K in parallel with this, that almost, but not quite, cut this in half, right? You're only going to have maybe about 20K or so, something like that. I didn't do the math, but that's what's going to be here. So you're going to get more of that signal into here. And what that's going to do is that's going to cancel out more of this side. That's what a differential input pair does. Because this is your inverting input, non-inverting input. When I increase the inverting input, it's going to decrease the output of the inverting input. Right here at this collector. All right, so what's the point in all of this, you ask? Okay, I've now removed that 33K resistor. Do you see it? And that's this feedback resistor right here that's going to our inverting input. And I've replaced it with a 250K potentiometer. So that's a lot more. Now, right now, as closely as I could get it, I set this pot to be 33K of resistance. All right, so let's turn it back on, and I'm looking right now at just the speaker output. So this is actually going to your speaker load right here, to the dummy load. And so we're reading right across our speaker terminals with an 8 ohm load on it. And if I turn this on, as you would expect, there's your output. And it looks pretty good, doesn't it? Not too bad. And I'm at 5 volts per division. So you can see I have about 3 volts, 3.5 volts RMS. It's coming out to just under 2 watts of power. So we're not driving it real hard. Now watch what happens when I increase the resistance of that pot. So I'm going to go up in resistance. So it's going to be higher than 33K. You see what's happening? Look at the gain of the amplifier, how high. And I can keep going. And I'm going to overload the amp, and there it's going into clipping now. All right, now I'm going to turn this off because I'm really pushing that amp pretty hard, and it's going to get hot really fast. But did you see how much gain this amp has now? So you might say to yourself, why do I want to put a circuit in there that cuts the power of my amplifier down? Well, that's where it's all going to get tricky here. Okay, looking up at the signal generator, I have a sweep signal set up. And all a sweep signal it would be like if I took the frequency knob manually and just rotated it up and down between a lower frequency and a higher frequency. That's what a sweep is. And I have the sweep set to go from 10 hertz, 10.000000 hertz, up to 48 kilohertz. That 48 kilohertz is more than double the audible range of an amplifier. But because of the feedback, because of things like that, you want the amplifier to respond linearly up there. So no matter what, though, if you go over to the output, it's always going to be outputting at these terminals. It's always going to be outputting 50 millivolts. So there will always be a 50 millivolt signal going into the amp. So really, no matter what frequency I feed into there, if it's at the same amplitude, I should get the same amplitude out. The amp should have the same amount of gain regardless of the frequency. That's what we're looking for, okay? So I have the gain, or that resistor here now, turned all the way up to almost 200K. Very high. So there's very, very, very little feedback. For all intents and purposes, we've almost, but not quite, removed all the feedback from this circuit. And let's see what happens now when we sweep the signal. Let me turn the light on here. Okay, let's go. So that started at 10 hertz and we're sweeping up to 48 kilohertz. What's happening to the amplitude of that signal? Do you see? I'm not changing the amplitude of my signal generator, but look at what the output to the speakers is doing. Crazy, isn't it? Okay, while that is happening, all right, I'm going to turn this off for a second. What I'm going to do now is I'm going to turn that sweep on, and I'm going to adjust this pot until you don't see any breathing on that. I call that breathing, you know, when the amplitude goes up and down, up and down. And let's turn it and see if we can get it to stop doing that. Okay, here we go. So I'm just going to turn this way down right now. And see, it's shrinking a wee little bit now. Do you see? But hardly at all. Very, very little. And I'll go a little bit more maybe. See if I can. This pot's real touchy because it's a 250K pot. Okay. And if I move this kind of in the middle here so it tracks between those lines, let's see how it tracks between these graticules here. So we're up to 48K, and see, it's just barely breathing a little bit. And I could take it down a little bit more, just like so. And see, now it's almost not moving at all. As a matter of fact, the volume is changing so little that your ear would not be able to discern that. Okay, so if I turn this up, you can see just how little it's dipping below that line. See, it's just barely touching it. And then when we go up to full volume, or to 10 hertz, it goes a little above. So much, much more linear now, isn't it? Okay, so I'm going to turn the amplifier off, and I'm going to remove this pot from the circuit so none of the circuitry interferes with it. And we're going to measure how many ohms this pot is. What do you think? Okay, so I'll just take one leg off so we can measure it. And we'll get our ohm meter out. Remember, we just did this by eyeball. And let's connect one probe here and one probe here. Look at that, almost 28K. Very close to that 33K resistor that's in there, isn't it? Very, very close. And we did that totally by eyeball. I didn't do anything. We didn't do any math, any calculations, anything like that. But you can see that's why that was chosen. Now by putting that 33K instead of a 27K resistor, the amplifier will have a little bit more gain on the bass frequencies than it will on the treble frequencies. So they did that on purpose. They wanted the amp to have a warmer tone. So if we increase that 33K a little bit, you'll get a little more bass in your sound signature of the amplifier. If I increase this resistance even more, let's say we took it down to maybe 18 or 20K, it would flatten that response out. Or it may even eventually get to a point where it would sound almost tinny because it would be restricting the bass even more. And remember, that's with a resistive 8 ohm load. So in other words, I have a resistor on here. A speaker doesn't act like a resistor. A speaker is reactive, so that the equivalent resistance changes with frequency. And if I put a different resistor on here, like a 4 ohm or 2 ohm, that signature would change ever so slightly. So that 33K is the compromise to give you the best, flattest frequency response under all conditions, and giving you a tiny little bit of boost in the bass frequencies. That's how that works. So that's a good compromise. And that's why they chose that. So that's it for this video. We basically looked at the waveforms in the input differential pair, and we looked at how that affects how the feedback affects that, and how that affects the whole circuit and affects frequency linearity. If the amplifier reacts differently, and if it amplifies more at certain frequencies than it does at other frequencies, it will create distortion. And that's how we reduce distortion, is through that negative feedback and that filter circuit. So R12, R10, and C4 are what allow that to happen, and implementing the use of a differential input pair. Now, other ways of doing it, which are not as good as this, would be to, instead of having this second transistor on this Class A input, you would just take this feedback network and connect it right here at the emitter, right in this bias point here at the emitter. And it would do the same thing, but it's not as good as having the differential input pair. And remember, these are all those janky transistors that came with this. This is a $12 kit or $15 kit, including the components and the board and everything. So and the heat sinks. So you can imagine these are not matched transistors. So again, you hear a lot of things about, how important it is to match these and everything. In some instances it is, but you can see it doesn't have as big of an influence on this as you might think. This is the most bare bones version of this type of amplifier you could possibly have. They've stripped it down as far as you can go. You don't even have adjustable bias. You don't have adjustable offset. Nothing. And yet, you're not using matched transistors. They're the wrong transistors. These aren't even complementary to the PNP. So a 9012 and a 9014 aren't even the same family. You're supposed to have 9012 and 9013s. So, but look how well this thing performs. And we haven't even modified anything yet. So I hope you enjoyed this episode here. In the next episode, we're going to look at this bias circuit a little bit, and we're going to see if we can identify crossover distortion and maybe how we can deal with it a little bit. And then later on, we'll try to do some mods and just see if they improve the amp or not. So until then, I wish you all peace, joy, happiness, and good health in your lives, and we'll see you again real soon. Take care, everybody. Bye-bye.